Okay, so this is the solution part of this problem. We kind of talked it through last time. First step in any problem like this is to understand the problem, which we did, and essentially we drew a high-level black box diagram in this thing. So the next thing is is to plop down the modules, and we kind of listed them in the last lecture. So we can just put them down here. So this one we know we got to be able to draw. We know it has a RAM. Anytime I have a RAM in a circuit, I know it's going to have a counter to drive the addresses of that RAM. This RAM is 16 by 8, so the address space is necessarily 4 bits, so it's going to be a 4-bit counter. And what's interesting on this counter, I'm going to need to be able to count up on that. I know that's going to be a control signal, so I'll go ahead and do that. I know it's a clock circuit as well as the RAM. I think I'm going to put a write enable in this just for the heck of it, because I can, rather than tying it low like I've been doing. And typically, I know someone's going to press the go button, and these counters, I need to start at 0, so it's going to have a clear control as well. Okay, so that's the RAM part. Any circuit that has a RAM is going to look like this. That should be first thing you do in these circuits. So on the outside of this thing, I know I'm going to have another counter that's going to count how many occurrences of 47 there are. So that's going to be my count. And it's a clock circuit, and I'm going to be able to somehow count up on this thing. It kind of clashes with that signal, but I'm going to call this, we'll say up to, how's that one? And the key to making this circuit work is the fact that it has a comparator in it. It's looking for 47. The way I'm going to look for 47 is using a comparator. And what I'm going to do is hard code one of those inputs to 47. Okay, so the issue on this thing is what's the comparator comparing to? It's going to be comparing it to the output of the RAM. Okay, the counter is going to start at 0 and step through this thing, and it's going to send the data over the compare to see if it's equal to 47. And I know it's going to be equal because we've got an equal output here that we'll take a look at. And looking pretty good. I know that anytime I start counting anything, I need to clear that counter. I want to start counting at 0 rather than whatever's in that count. So the counter here, this output counter is also a register. That means I can, when I'm done, I can just turn the count off on this thing. Okay, so I got to put some extra notes in here. Lastly, every time I use these problems, I got to know when the counter's timing out. And so this is the counter here that steps through the RAM. So I need to know when I'm done stepping through the RAM. This ripple carry out signal is going to turn on when I hit 15. That's going to tell me I'm done. And looking good here, I need to specify, I got all these control signals here and status signals. I need to collect them all. So up to and up are control signals. Up to. What else do I got? It looks like I got a clear. The clears are shorted together. And do I need anything else? Looks like I have a write enable since I decided to put that in there. So we'll put that in there too. So there's 4 control signals on this thing. And as far as the status goes, it is clocked. I don't need to put that in there. I have an RCO, which is my important one. And certainly I have a go signal. Okay, so I think I have the whole circuit set up here. The idea here is that I noticed I did not route the clock signals. That would make it messy. I did not route the control signals either. I could have connected. You know, the idea here is, like, for example, this WE is connected to this WE. If I put that in there, it'd be really ugly. It'd be even more messy than it already is. So if looking at this thing, I'm trying to figure out what the state machine is going to look at, and I'm thinking, okay, it's doing two things. It's waiting for a go signal, and it's waiting for that go signal. It's actually outputting the previous count it had. So that's one thing. The next thing I will be doing is looking for those 47 once someone presses the go button. So those are my two main functions here. It pretty much implies I need two states in this thing. So once again, I could use 3 states and put a kind of initialization state in there, but typically I get around that by using a Mealy machine rather than a Moore machine. Okay, so here we go. Here are my two giant states. Give them some meaningful names. Wait and a count state. And so let's do it. This is my wait state. Inside this wait state, I'm going to go through these signals here. I know for sure in this circuit, the circuit never has to write the RAM, so I'm going to go ahead and turn the write enable off in both these. So while it's waiting for a signal, certainly I'm not going to be doing anything with either up input. So I don't have to worry about that. And the issue is the clear input. So I've got 3 signals here. I have to worry about the clear. So the clear, I'm going to put it as part of make it into the Mealy machine. I'm saying so long as the button's not being pressed, I am going to keep that clear off. But once someone presses the button, I am going to turn the clear on. So that's go CLR. So that means as a Mealy machine, when that button, that go signal gets asserted, the clear signal is going to turn on. It's going to clear the counter, but it's going to clear both counters. The clear signal is shorted on both counters. What's that? Okay, and anyway, that looks good. I have 1, 2, 3, 4 signals here. I've treated the clear as a Mealy output on this particular state, which is fine. And so we're done with the state. So let's go to the next state, and we have a clear. And certainly while I'm counting, I don't want to be clearing this thing, so I'm turning the clear off. But what I'm interested in is I got the 2 signals here, the clear and write enable, but I need to know what to do with the 2 up signals. Okay, so the 1 up signal is going to be driving this counter here, and it's always going to be counting up, so I'm going to leave the count on in that thing. But what's interesting here is what to do with the other counter. And so what I'm going to say here is this counter here increments when I find that numbers are equal, and when I find the numbers are equal, it's going to be it's going to indicate that with the this output of the comparator. So essentially the up 2 equals the equals signal. I'm going to run out of space there. Okay, so that's kind of messy, but we'll do that, make it cleaner just to be sure. Oh. Up 2 equals EQ. Okay, so what's going to keep me in this state is the fact that RCO is turned off. What's going to cause me or allow me to transition back to the wait state is the fact that RCO is going to turn on. Okay, so once again, for each of these states, I accounted for each of the four control outputs here. Technically speaking, I guess I'm mostly done with this. I should put some notes on this, and we'll say up equals 1 is an increment. Up equals 0 is a hold. And I'm going to say the same thing for this one. And I should always do these problems to make that super clear. The other thing I'm going to say here for counters, clear has precedence. Precedence, I can't spell it, over the up signal. And with that, I'm going to call it done.